Hello, everybody, and welcome to our final lecture of the semester. Uh, it's been a strange semester, but I hope that you've been enjoying these lectures. I really I really enjoyed it. I quite like teaching this class. I hope that you think I did well as well. Good. So today we're going to continue talking about the traveling salesman problem that we began talking about yesterday. So I'll start off by saying that today. Traveling salesman problem. Continued. Okay, and I wanted to remind you about the different kinds of graph theory that we're using at the moment. So recall here we consider Hamilton circuits rather than Euler circuits. And what is a Hamilton circuit? Well, this is a circuit in the graph. So you start and end at the same vertex, and you visit every vertex in the graph exactly once and end back where you started. So I'll write that down. Definition: a tour or Hamilton circuit in a graph G is a circuit which starts and ends at the same vertex. So this is a bit redundant. That's in the definition of a circuit, is that it starts and ends at the same vertex. And visits every other vertex exactly once. Okay, so these are kind of like Euler circuits, but different in the sense, remember, these are different than Euler circuits, where every edge has to be used once. So let me give you a couple examples of these and how they would differ. Our first example, what if we had this graph? Okay. We'll say A, B, C, and D. Okay. Well, the first question, does this have an Euler path does this have a Hamilton circuit? Okay, so we can just try them all. If we wanted maybe we start at A, and we go there, and we visit this vertex. Oh, now we're stuck. And similarly, if we start there, then we can't go back there because that visits that vertex 2 times. So this has no Hamilton circuit. Since once we visit D, we are stuck. In fact, if I'll say this fact, a graph with a degree 1 vertex can never contain a Hamilton circuit. Okay. So that one can't contain a Hamilton circuit, and it also doesn't have an Euler circuit, because remember, we needed every vertex to have even degree in order to contain an Euler circuit. So D, again, we get stuck. We can't get back to it without using this edge twice, and we can't get back to it either without using this vertex twice. Okay. Now I want to give you a slightly different graph. I'll do it like this. It's a bit ugly. Okay. So there's our graph. Oh, it's not pretty. Okay. So there's our graph. And now we want to know, how about a Hamilton path? A path visiting every vertex once. Okay, well, let's see. If we start here, then we can go down, visit that vertex, over and visit that vertex, down there, over there, and down there. And sure enough, we get a Hamilton path. So this is what we call a Hamilton path, yes. So I'll do it. Shoop, shoop, shoop. Okay. Yes. Alright. But does it have an Euler path? I'll go back to black. Well, I'll let you think about that for a second. What did we need for a graph to have an Euler path? We wanted every vertex, except for 2, to have even degree. But here, we have this one with odd degree, and this one has degree 3. See, there's 3 edges. And this one has degree 3. And this one has degree 3. And this one. In fact, every vertex has odd degree. So the answer is no. Every vertex has odd degree. And you can try it out. I'll write that here. Okay. And final example is K4. This is the graph on 4 vertices where every vertex is connected. So we connect those ones. Good. Okay. This is also known as AKA the complete graph on 4 vertices. Okay. Now this is a kind of interesting example because I was talking yesterday about how every complete graph has a Hamilton cycle. Now I wonder if you can see why. The answer is that every complete graph, you can draw the vertices around in a circle. And since every vertex has to be connected, you can just, you know that all of these edges have to be part of your graph. And so that means that we can always find a cycle like that. So here, that cycle corresponds to this. So I'll say has a Hamilton cycle I'll just draw it in. But does this have an Euler cycle? No. Not have an Euler cycle. Because if ever we try and do every edge exactly once, that's what we want to start at one vertex, trace every edge exactly once. Doesn't matter if we go to the same vertex twice. We just want to trace every edge exactly once and get back to the start. So let's try it. We go down here, and then maybe we go over here, and then we go up here, and then we go over there, and now we're stuck. Can't get to the last edge, can't get back home without retracing an edge. And moreover, it doesn't have an Euler cycle because a graph has an Euler cycle only if and only if every vertex has even degree. And I'll remind you what I mean when I say if and only if. What I mean in this sense is that, so, if and only if. This means that if a graph has an Euler cycle, then I know that every vertex has even degree. And if I know that every vertex has even degree, then I know that the graph has an Euler cycle. All right. So now I want to say some facts about complete graphs. Oh, right. So no, K4 has no Euler cycle. Okay, so yes, now I want to say some facts about complete graphs because I think they're fun to count things on and yes. So first, maybe I'll draw some for you. So here, let's start with the basics. K1 is just going to be one vertex connected to itself. I have K2, which is going to be two vertices, and they're going to be connected by an edge. Okay. We're going to have K3, which is going to be three vertices, all of them connected, and that makes a triangle. So a complete graph on three vertices is actually a triangle. Next we're going to have K4, which we just saw. I'll start making these okay. So that's 1, 2, 3, 4 vertices. And if you don't like the crossing lines, we can draw K4. Remember, K4 is planar. So we'll do a little isomorphic symbol, and we can also draw this like this. And I was just thinking about this last night. What's cool about this graph is that it kind of, so K4, alright, so look at this. If we draw some axes, right? So if we draw in one dimension, and here's 0, and here's 1, and here's, yeah, let's just do 0 and 1. Okay, then what we get is a K2. And if we draw our axes like this, and we put a 0 there, and we put 1s on each of our axes, and connect all of the dots, what we're going to get is a K3. Now look at this. If I draw in 3 dimensions, no. People usually like 3 dimensions like this. Okay, so imagine this is like the corner of a wall. So this is our X, our Y, and our Z axes. So now if we put a point at 0 and a point at 1 on each of these axes, and I reposition where I put 0, and then I connect all of these lines, look what I get. I get K4. Now, who can picture what K5 looks like? Okay. What K5 looks like is this. Oop. And remember, K5 is our first non-planar graph. And so I wonder, if you put 1s on all of the axes in 4-dimensional space, would you see something that looks like a K5 positioned in some way? I don't know. These are interesting questions. And finally, I want to do K6 here, because why not? Here's another way of drawing it. You can put them on a circle and go 1, 2, 3, 4, 5, 6 for K6. And then you can just draw all of the guys here, connecting them. This one, this one, this one. Am I missing one? Yes. Okay. And missing this one still. Okay. And so this is the graph we get. This is a K6. Make the vertices nice and big so you can't see all of the bad things that are happening. Okay. So there we have our K6. Now what are some facts about these? The first fact I want to note about complete graphs is, well, so fact 1. Kn has n vertices. Okay, so this may be a pretty simple fact. I don't think I have to argue that. Fact 2. Every vertex of Kn has degree n minus 1. This is because if you start at this vertex and you want it to be connected to every other vertex, well, how many vertices are there that you can go to? There's 1, 2, 3, 4, 5, which is 6 minus 1. Good. Third, slightly more interesting question. How many edges are there in Kn? Well, now I want to get back to, so remember the complete graph includes every possible edge. Kn has every possible pair of vertices for an edge. How many ways to make pairs of n objects? We've done this earlier this semester, so things should be coming back. Well, we have n options for the first thing in the pair, n options for first object. And then once we've got that one, because we can't pair it up with the same vertex, we have n minus 1 options for the second. Object. So that's going to make our pair, right? But if we don't care about the order that we have things in, if having Jill and Brian together is the same thing as having Brian and Jill together, we divide by 2, because we will have counted every pair exactly twice. So Kn has n times n minus 1 divided by 2 edges. We're going to use this when we count Hamilton paths and circuits. Good. So now we're going to go back to the traveling salesman. So I'll do a little note. How many ways for the traveling salesman to visit every city? And I'll let you think about that. I'll stop the video and come back with another one. But hint, think about how many ways to order the sites or the cities on a list. And I'll stop the video here and start another one on the traveling salesman.